In this part of the episode, we are going to be talking about exponents that are zero and exponents that are negative. And as we work toward that, let's begin with a warm-up exercise. Someone says to me, simplify in the numerator x to the power 7 and in the denominator x to the power 4. Now, let me begin in this problem using the same technique that we learned in part 1, where I will, in the numerator, write out 7 copies of x multiplied together, and in the denominator, write out 4 copies of x multiplied together. So every time I see a multiplied x in the numerator canceled out by one of these divided x's in the denominator, that multiplied x and that divided x will cancel each other out. So I get to cancel out 4 of those x's in both the numerator and the denominator, which leaves me with x to the third power in the numerator and a 1 in the denominator that doesn't actually accomplish anything. Now, notice what's happened here. I had 7 x's in the numerator, and I removed and I deleted the 4 x's that were in the denominator. And I was left with 3 x's, 3 being the difference of the two exponents, the 7 in the top, take away the 4 in the bottom. And so this observation gives us one additional exponent property to add to the list of 3 exponent properties that we wrote down in episode number 16. We had these exponent properties that helped us when we were multiplying expressions that contained exponents on variables. And now we will have another exponent property that will help us when we are dividing expressions that contain variables. If I am dividing expressions that contain variables, for example, I have some base to some power up here divided by the same base to some other power down here, then I can simplify that expression by just taking that base and subtracting the two exponents. Because of the cancellation that happens here, if you have 7 x's in the numerator, 4 x's in the denominator, then 4 of those x's cancel out, and you're left with only 3, 7 minus 4. So that is the reasoning that leads us to this property here. So to give you an example of this property at work, suppose that I had x to the power 25 divided by x to the power 18. I really would not want to have to write out 25 copies of x in the numerator and 18 copies of x in the denominator. So instead, for exponents that are this large, I'm going to go ahead and use the exponent property, which says if you want to divide x to the 25 by x to the 17, all you have to do is subtract the two exponents, 25 minus 18. 18 of the x's will cancel out, leaving behind 25 minus 18, leaving behind, if I have that right, 7. 7 copies of x will be left behind after 18 of the x's are canceled. Now, what if I tried to apply that same exponent property in this case? X to the 20 over x to the power 71. If I just went ahead and tried to apply that same exponent property to this expression, I would go ahead and write down x to the power 20 minus 71, subtracting the top exponent and the bottom exponent. But this would leave me with an exponent that's negative, x to the power negative 51. And this is interesting, right? We've never seen negative exponents before. But so what could be the meaning of something like this, x to a negative power? Well, if I think about this situation, I can see that in this fraction, I have many more x's in the denominator than I have in the numerator. So when I do the cancellation, the x's that are left behind will be left behind in the position of the denominator. To give us another example with slightly simpler numbers, if I had x to the power 3 divided by x to the power 5, And if I did this problem the old-fashioned way, writing out all the copies of x manually and canceling all the x's that are both multiplied and divided here, this would leave me with two x's in the denominator of the fraction and a 1 in the numerator of the fraction. If I compare that to what I get by applying the exponent property at the same time, if I did x to the third power over x to the fifth power by subtracting the two exponents, then that would be x to the power minus 2. So if these two actions are supposed to be just two different ways to get the same answer, then these two expressions right here, x to the power minus 2 and 1 over x squared, must be the same answer, just in different formats. In other words, in order to make sense of x to the power minus 2, we can make sense of that by thinking about that as the reciprocal 1 over x squared. Negative exponents have the same meaning as reciprocals. So to summarize that, if someone says to you, I'm thinking about a base and raising it to a negative power, like x to the power minus n, then that's the same thing as taking the reciprocal of b to the power positive n. In the same way that x to the power minus 2 is the same as 1 over x squared, x to the power negative 51 would be the same thing as 1 over x to the power 51. 51 copies of x multiplied together in the denominator of a fraction. So this is how we make sense of negative exponents. Negative exponents have the effect of applying a reciprocal. So now we understand the meaning of positive exponents as repeated multiplication and of negative exponents being essentially repeated division, dividing by several copies of x. But there's one kind of exponent we haven't talked about yet, which is what if the exponent is not negative or positive? What if the exponent is exactly 0? If the exponent is exactly 0 and you raise a number to the power 0, the result of that is always equal to exactly 1. And for just a brief explanation of why this property is true, if I took, for example, x squared divided by x squared, when I divide something by itself, the result of an action like that is always equal to 1. But at the same time, if I did x squared over x squared using the exponent property, that would be x to the power 2 minus 2. That would be x to the power 0. So these two answers, they're the same answer to the same question. They were just obtained by different methods. So these must be the same number, just expressed in different formats. So negative exponents have the power of making reciprocals, and 0 exponents always create a result of 1 unit. Let's practice using these properties in a couple of different exercises. Someone says, what is the value of 2 to the power 0? Anytime you have an exponent of 0, the result is equal to 1. 2 to the power 0 is equal to 1. Someone says, what is x to the power 0? X to the power 0, once again, as soon as you have an exponent of 0, the answer to that is 1. X to the power 0 is 1. Someone says, what is 4 to the power negative 1? So 4 to this negative exponent. 4 to the power negative 1 says take 4 to the power positive 1 and take its reciprocal. Put it in the denominator of a fraction. Now, if I take 4 to the power positive 1, 4 to the power positive 1 is just a single copy of 4. So 4 to the power negative 1 is just 1 over 4. 4 to the power negative 1 is just the reciprocal of 4. Someone says simplify 3 to the power negative 2. So here I have that negative exponent. So instead of multiplying two copies of 3 together, I'm going to essentially divide by two copies of 3, 1 over 3 squared, the reciprocal of 3 squared. And 3 squared being equal to 9 means that 3 to the power minus 2 is the same thing as 1 over 9. Someone says, what about x to the power negative 13? X to a negative power is the same thing as the reciprocal of x to a positive power, 1 over x to the power 13. And someone says simplify x to the 20th over x to the 71. I subtract those exponents using the exponent properties. And now I know that x to the power negative 51 is the same thing as 51 copies of x in the denominator of a fraction. This would be equivalent to 1 over x to the power 51. 51 x's left in the denominator after canceling.